Hello and welcome to this tutorial on deriving the equivalent circuit for an induction machine. Again, we just need to reconsider the induction machine. We've got in a simple two-pole machine, we've got our 6 poles with their windings around them and our rotating rotor. And we'll call these A, B, C, A dash, B dash, and C dash. To start developing this is all we really need to think about. We basically have a coil of wire on the outside and a big lump of metal on the inside. And coils of wire wrapped around pieces of laminated steel and big lumps of metal have resistance and they have inductance. So the first stage of understanding this is to just do that. We can say we've got a big hunk of wire around the outside with a whole lot of stuff going on and a big hunk of metal on the inside with a whole lot of stuff going on. And what we can do, like we do with a lot of equivalent circuits, is we idealize things. So we will make this an ideal perfect hunk of metal. And in order to do that, we take all the resistance and all the inductance values out of it. And this is going to be this is the stator, so we're going to call this R1 and X1. So this is all the resistance out of the stator and all the inductance out of the stator and the perfect stator. And we do the same with the secondary, with the rotor. We take all of those values out and we have a perfect rotor with all the inductances brought out here and all the resistances brought out here. And now that's perfect. Now, what it is you've got a perfect coil of wire inside another, well, a perfect hunk of wire, or sometimes it's coils, inside another coil of wire. This is what we've got over here, which sounds very much like a transformer. So, what we can then do is we can replace this perfect set of wires with the transformer model. So this is our first stage. Our second stage is to redraw it, but with a transformer in there. So here's our R1 still and our X1, and then we come up and then we do our transformer. And we've got our magnetizing resistance, our magnetizing reactance, our idealized transformer with a turns ratio of whatever it is, and then we've still got our secondary values over here. Now, obviously we're trying to build in a model for an induction machine, so we're not interested in this transformer. So what we can do is we can get rid of it. And the effect of the turns ratio, we can declare that in these, not by using N, but by basically just calling these kind of X and kind of R. And so that takes us down to the third stage of our circuit. Again, this stays the same, R1, X1, our magnetizing resistance, our magnetizing reactance. We're not going to have a transformer in there anymore. Oh, that's meant to be a resistor, sorry. And so instead of calling this X2, we call it X-2, and this is now R-2. So what we've done is we've got rid of that. And we've used it by using the superscript terms here. Now, there's one other thing we need to factor in, and this is a bit of a, the reality is it's a bit of a bodge, okay? It's just done to make things work, and that is we need to think about slip. And some people discuss the slip component here, other people discuss it here, but what we need to do is we need to put the factor of slip in. And I've talked about slip in previous ones. Slip is the difference in speed between the rotating shaft and the magnetic the rotating field that goes around here, and it's a ratio, and it's expressed in the circuit diagram as being a denominator to the secondary resistance, and it works quite well. Right, the third step is to acknowledge the reality that this magnetizing resistance here, Rm, is really so high as to not really matter. And because it's a very high impedance, it's effectively an open circuit. So we end up with our final stage of our equivalent circuit as being R1, X1, a magnetizing resistance, Xm, as well as the secondary X-2 and the secondary resistance R-2 over the slip. And that is the development of your basic equivalent circuit for an induction machine. Yes, there are other circuits available that look at different things, but for 95% of the work that almost everyone will do, this circuit and the things about it will be an adequate model. It's not perfect. This sort of circuit won't do a very good job of looking at transients or extreme conditions or startup conditions and, you know, down into the minutiae. But it does a perfectly fine job of basic power analysis. You can see here that, you know, you could measure the voltage here, the current here. The impedance would obviously be these two here in series with these two in parallel with the magnetizing reactance. So I'll put up another video on how to go through and how to find these things out by doing a DC test, a locked rotor test, and a no-load test. By doing those tests, we can then go through and find out what these values are. But frankly, I've run out of paper, so we're going to have to do that on another tutorial. Thank you very much for watching. Look forward to seeing you again.